Hey everyone, welcome to This Explainer. Today we're diving straight into the really fascinating world of non-destructive testing to completely demystify the exact science of the magnetic yoke. If you've ever found yourself wondering exactly how industrial inspectors guarantee the safety of those massive metal structures we interact with every single day, well, you are in exactly the right place. So picture this. You're inspecting a freshly welded structural plate on a supercritical piece of infrastructure. To the naked eye, the weld looks absolutely perfect. But here's the catch. How do you expose a truly microscopic crack hidden deep in that solid steel without completely destroying the part to find it? Obviously, you can't just smash it open. You need a method that's reliable, highly portable, and incredibly sensitive to surface discontinuities. Here's our agenda for today's inspector journey. First up, the science of the yoke. Then we'll hit the lifting test math, walk through a practical field inspection, and finally wrap up with the art of demagnetization. All right, Section 1, the science of the yoke. Let's look at the actual physical principles that make this incredible inspection possible. Meet what is arguably one of the most vital pieces of equipment for field testing in the entire industry, the handheld, portable, articulating magnetic yoke. It's a super versatile C or U-shaped unit. And because of this clever design, an inspector can easily test parts with really complex geometry, almost any size in some seriously challenging locations. But how does this relatively simple-looking tool actually generate a magnetic field strong enough to reveal those hidden flaws? Well, the secret is literally on the inside. You've got a conductive coil wrapped tightly around a soft ferromagnetic, basically iron core. When you pump current through that coil, it magnetizes the core material, producing this incredibly powerful longitudinal magnetic field that flows right between those articulating legs, or poles. It acts a whole lot like a conventional bar magnet. And because those legs pivot, you can adjust them to make solid contact with weirdly shaped surfaces, driving that magnetic field straight into the steel. Now, these units are incredibly versatile when it comes to power, too. A lot of them simply plug right into standard AC wall outlets. But let's say you're totally off-grid, maybe scaling a scaffold or crawling into a tight, confined space. In those situations, they can actually run on half-wave DC power using portable battery packs. Some of the really high-end units even feature a selector switch, letting the operator toggle between AC and DC depending on the specific job. Oh, and fun fact, AC is actually fantastic for demagnetizing the part later on because its rapidly reversing polarity essentially scrambles any leftover magnetic field. Moving on to Section 2. The lifting test math. Because before we can even think about trusting this tool to find life-threatening flaws, we absolutely have to prove mathematically that it works. Look, you simply cannot assume your yoke is working just because the power light flickers on. To properly calibrate an AC yoke, you've got to set the legs exactly 2 to 4 inches apart, place them flush against a standard test block, and energize it. At that point, it must lift exactly 10 pounds of steel. Not 9, not 8, exactly 10 pounds to pass the ASTM standard requirements. If it drops that weight, its electromagnetic strength just isn't up to par for a safe inspection. Simple as that. But if you flip that switch to DC power, the math shifts entirely. See, DC magnetic fields penetrate much, much deeper into the steel compared to AC fields, which kind of just hug the surface. So the standard is way stricter. For DC, the legs must be placed exactly 6 inches apart, and the yoke has to lift a massive 30 to 50-pound weight. Passing the specific lifting test is a non-negotiable, absolute requirement before any critical fieldwork can even begin. But wait, the yoke itself is really only half the equation here. To ensure we can actually see the microscopic flaws we're uncovering, the inspection environment has to meet some incredibly strict lighting requirements. You need a calibrated light meter to verify a visible light intensity of exactly 1076 lux, which, if you're wondering, equals exactly 100 foot candles, right at the inspection surface. Because think about it, we're hunting for microscopic indications. If your lighting is garbage, even the absolute strongest magnetic field won't help you spot the flaw. Okay, Section 3, Practical Field Inspection. Let's see how all of this physical science actually translates into a real-world, step-by-step inspection on a welded plate. This procedure is an incredibly precise, carefully executed sequence. Step 1 is prep. You absolutely must clean the part completely using a solvent cleaner so it's totally free of dirt, oil, or grease. Step 2, you apply a thin, even coat of white contrast aid paint to the weld in the heat-affected zone. But a quick heads up here, if you spray that coat too thick, you actually have to clean it all off and start completely over because thick paint will literally hide the flaws. Step 3, place the yoke on the part, energize it, and liberally apply wet, visible black particles right between the legs. That white paint gives you a stark background so those black magnetic particles pop clearly when they get sucked into a crack. Finally, you inspect for indications and record any discontinuities you find, usually marking them up in red on a part diagram. Now, since magnetic particles only gather at flaws that disrupt the magnetic field lines, the orientation of the yoke is literally everything. You have to walk the yoke successively down the entire length of the weld in a 45-degree crisscrossing pattern. Why? Well, this multi-directional approach guarantees that no matter which way a tiny crack is hiding, whether it's running dead straight along the weld or horizontally right across it, the magnetic field will hit it perpendicularly and force those black particles to bunch up right there. The crucial, absolute must-do point here is coverage. Every single magnetizing shot you take as you walk that yoke down the weld has to overlap the previous one by a minimum of 10%. This ensures absolutely no dead zones form between your placements, guaranteeing that no microscopic flaw manages to escape detection. It is a highly systematic, insanely thorough process. Finally, Section 4, the art of demagnetization. Because once our hidden flaw is revealed, measured, and recorded, our job still isn't quite done. We have to safely pull out the residual magnetic field we just pumped into that steel. If we leave a part highly magnetized, it can completely wreck future machining or welding processes. So, using the AC capabilities of the yoke, inspectors can efficiently demagnetize the piece. You've got contact methods, like placing the energized yoke right on the surface and giving it a twist, or just dragging it away. Then there are non-contact methods, where the part is simply passed between the yoke's poles and pulled away while it's still energized. And to wrap it all up, a field indicator is used to verify that the magnetism is truly 100% gone. As we wrap up this explainer, I want to leave you with a thought to chew on. The entire built world around us relies so heavily on the unseen diligence of these NDT processes. So the next time you drive over a massive steel bridge, ride up in a high-rise elevator, or fly in a commercial plane, ask yourself, did the inspector's yoke pass the 10-pound test? It's that rigorous math, the strict step-by-step procedure, and the sheer science of the magnetic yoke that quite literally keeps our world standing safely. Thanks for joining me on this explainer, and keep questioning how the world works.